Hello, my dear students. Welcome to Chemistry with D K Sarma Sir.
So, dear students of class 12, today we are going to discuss your organic part. The first chapter is Unit 10, Halogen Derivatives. Halogen Derivatives of Alkanes or Arenes. So, let us begin. We all know what are organic compounds. Organic compounds means hydrocarbons or their derivatives. So what are hydrocarbons? Hydrocarbons are binary compound of carbon and hydrogen. Hydrocarbons may be of different types. We all know that. Say methane. This is a hydrocarbon. C2H6 ethane. This is also a hydrocarbon. Similarly, benzene C6H6, this is also a hydrocarbon. Naphthalene, say C10H8, this is also a hydrocarbon. Now, hydrocarbons belonging to this category, these are called aliphatic hydrocarbons. And hydrocarbons belonging to this category, these are called aromatic hydrocarbons. Okay, so what are halogen derivatives? In halogen derivatives of organic compounds, one or more hydrogen of the hydrocarbon is replaced by halogen. We all know what are halogens. Halogens are the elements in group 17 of the periodic table. These elements are fluorine, chlorine, bromine, iodine and astatine. 80. For now, we will not consider astatine as halogen. Why so? Because it is not actually a true halogen. Unlike the other halogens, this is a metal. So, we will not consider astatine here. Now you see, one or more hydrogen in an alkane or any other hydrocarbon may be replaced by any of these four halogens. So, such compounds will be termed as haloalkanes or haloarenes. You look. Say this is methane. By extending the structure of methane, we may write this CH4. Valency of carbon is 4. It is tetrahedral carbon. 4 hydrogens are attached with carbon. Okay. Now, if we replace one hydrogen by halogen, for now we will represent halogen as X. What is X? This is a halogen. This is a halogen. Now, in this case, one hydrogen of methane get replaced by what? Halogen. So, this is called a mono haloalkane. Mono haloalkane. Similarly, we may replace two hydrogens. If we replace two hydrogens, what will be this? This is a dihaloalkane. In a similar manner, we may replace another halogen. In that case, it will be trihaloalkane. The last hydrogen may also be replaced. This will be tetrahaloalkane. So, from methane, if we consider chlorine as the halogen, we will get CH3Cl. What is this? This is chloromethane. This is chloromethane. we may have CH2Cl2. It is dichloromethane. We may have CHCl3. This is trichloromethane. And finally CCl4. What is this? This is tetrachloromethane. Now you see dichloromethane. This is IUPAC name. In common system, this is called as methylene chloride. This is called chloroform. And this is what? This is carbon tetrachloride. This is carbon tetrachloride. So starting from methane, we may have chloromethane by replacing one hydrogen by chlorine, dichloromethane by replacing two hydrogens by chlorine, trichloromethane by replacing three hydrogens by chlorine, and tetrachloromethane by replacing all the four hydrogens by chlorine. So in this way, this is called a monohaloalkane. It is dihaloalkane. This is trihaloalkane. This is tetrahaloalkane. So methane, what is methane? This is the simplest hydrocarbon. It has only one carbon and four hydrogens. If we consider some other alkanes or hydrocarbons, then the number of halogen derivative will be again higher. Now let us discuss the different types of halogen derivatives. Types of halogen derivatives. First of all, we know that in halogen derivative of hydrocarbons there is a CX bond, is it not? Carbon and halogen, these two are linked by means of a covalent sigma bond. Now depending upon the type of hybridization of this carbon, we may have two types of halogen derivatives. First one, the carbon is sp3. First one is the carbon is sp3 carbon linked with halogen. sp3 carbon linked with halogen. In this side, we may have say alkyl halide or sometimes this is called haloalkane. Here, halogen atom is directly linked to sp3 carbon. For example, so this is number 8. For example, CH3Cl. This is chloromethane. So CH2Cl. This is chloroethane. These are of this type. Number 2, allyl halide. You see, what is allyl position? The position 3 with respect to a carbon-carbon double bond is called allyl carbon. So consider this CH2 double bond CH single bond CH3. What is this? This is propene. In propene, you see, this is carbon number 1, carbon number 2, this is carbon number 3. So position 3 with respect to double bond, with respect to alkene, this is called allyl. So here you see, this is a methyl group CH3. This carbon has 3 hydrogens. If we reduce one hydrogen and the valency of carbon is satisfied by chlorine, what is this? This is allyl chloride. Allyl chloride. In IUPAC you will call it 1, 2, 3, 3-chloropropene. 3-chloropropene. This is actually in simple form allyl chloride. So we are going to study the types of halogen derivatives. The first type is sp3 carbon linked with halogen. In this case we get two types now. Number one, alkyl halide or haloalkane. For example, chloromethane, chloroethane, or say bromomethane, bromoethane. This is allyl halide. Here, this carbon is sp3. You look, this carbon is sp2, is not it? This carbon is sp2. This is also sp2, but this is sp3. How can you know that? How can you know the type of hybridization of a carbon? See, a carbon atom with 4 sigma bonds is sp3 hybridized. Okay, a carbon with 4 sigma bonds is sp3 hybridized. A carbon with 3 sigma bonds and 1 pi bond is sp2 hybridized. So remember these points. And finally, number 3, a carbon with 2 sigma and 2 pi bonds is sp. So in this case, you look at this carbon. This carbon has, look, 2 hydrogens attached with it, means 2 sigma bonds, and this carbon is also connected with this carbon by means of a sigma bond. So this carbon has 3 sigma bonds, 2 with hydrogens, 1 with carbon, and there is a multiple bond between the 2 carbons. The multiple bond means double bond means 1 sigma 1 pi. So it has, this carbon has 3 sigma and 1 pi, therefore this is a sp2 carbon. Similarly this one, but here the case is different. In this case the carbon is connected to 4 sigma bonds. Look, 2 hydrogens, this is carbon carbon, this is carbon chlorine, 4 sigma bonds, so this is sp3. Okay, so we have 2 types of haloalkanes belonging to the first type. Come to the third type, number C. It is benzylic halide. Benzylic halide. See, we all know what is this. This is benzene. What is this? This is toluene. So actually what is toluene? Toluene is methyl benzene. This methyl group is attached to a ring carbon, sp2 carbon. But this carbon is not sp2. It is sp3 because it has 4 sigma bonds. 1, 2, 3, 4. 3 hydrogens plus this. So this is sp3 carbon. Now if we reduce one hydrogen here, it becomes CH2. And that valency, if it is satisfied by say chlorine, this will be called benzyl chloride. Benzyl chloride. So based on the type of hybridization of carbon, we are going to classify the different types of halogen derivatives. In the first type, we have got sp3 carbon linked with halogen. There are 3 types: simple alkyl halides, allyl halides, and what? Benzylic halides. Now let us pass on to the second type. Here, sp2 carbon is linked with halogen. sp2 carbon linked with halogen. See, here we have two types. Number A, phenyl halide. Position 2 with respect to carbon-carbon double bond. This is called phenyl. Sometimes position 1 may also be considered as phenyl carbon. Phenyl position. You see, CH2 double bond, CH2. This is the simplest alkene. It has only two carbons. If this is carbon number 1, this is carbon number 2. Now, state of hybridization of this carbon is sp2. We are examining. There are 3 sigma bonds and 1 pi bond. Here also 2 plus 1 3 sigma bonds and a pi bond. Now, if one hydrogen is replaced here by chlorine, either in this side or in this side, this will be phenyl halide. So, phenyl halide is a type of this category. Number B, this is aryl halide. Aryl halide. We all know that aromatic carbon is sp2. In aromatic compounds, the state of hybridization of carbon atom is sp2. Now, if we see, all these carbons have one hydrogen each. So each carbon has 3 sigma bonds and 1 pi bond. Now, if that hydrogen is replaced by a halogen, this will be an aryl halide. This particular compound is called chlorobenzene. So in this way, it is possible to classify the different types of alkyl halides. First type of classification is based on the number of halogens. If the number of halogen atom is 1 in a compound, it will be called monohaloalkane. If there are 2 halogens, it is called dihaloalkane. Similarly, mono, di, tri, etc. we may have that type of classification. Again, we may have systematic classification based on the type of carbon, nature of carbon. So we have broadly we have 2 types. One is sp3 carbon linked with halogen, and the other is sp2 carbon linked with halogen. When sp3 carbon is linked with halogen, we have 3 subtypes, and when sp2 carbon is linked with halogen, we have 2 subtypes. Now you see, alkyl halides constitute a very important class of organic compounds, because if we examine, we will have several important uses of it. You all know about DDT. It is not. What is DDT? Do you know? What is DDT? DDT. It is dichloro, diphenyl, trichloro, ethane. Dichloro, diphenyl, trichloro, ethane. This is actually its common name. So basic structure is what? Ethane. Basic structure is ethane. Say we have 3 chlorines here. This group is called phenyl group. If we put a chlorine here, it is 4-chlorophenyl. This is the structure of DDT. What is this? This is an alkyl halide or halogen derivative of organic compound. Because you see here 1, 2, 3, 4, 5. There are 5 chlorines. Actually, this is the common name. In IUPAC, you will name it in a different manner. Actually, what is this? This is carbon number 1, this is carbon number 2. At carbon number 1 there are 3 chlorines. So what is this? 1 1 1 trichloro. Then at position 2 there are 2 groups. What group? Phenyl group with a chlorine at position 4. 1 2 3 4. 1 2 3 4. So 1 1 1 trichloro, 2 2 bis. Since there are 2 groups, we will use bis instead of di. 2 2 bis. 4 chloro phenyl ethane. This is the Iupac again. 1 1 1 trichloro, 2 2 bis, 4 chlorophenyl ethane. This is what? This is a commonly used insecticide or pesticide. Insecticides or pesticides are used to control pests, to control different types of insects. So DDT is a very important compound, but it is environmentally hazardous. It can cause environmental pollution. Another such compound is chloroform. This is an important compound. Its structure is very simple, CHCl3. In Iupac system it will be called trichloromethane. Now what is chloroform? Chloroform is an anesthetic. So BHC. This is also a useful compound of alkyl halide or haloalkane, halogen derivative of alkene. What is this? This is BHC, benzene hexachloride. Actually, it is not benzene hexachloride because no benzene structure is there, but commonly people call it BHC, benzene hexachloride. This is also a insecticide. It is used in the trade name Gamaxine. Now, let us have some discussion on the Iupac naming of halogen compounds. Iupac naming nomenclature of halogen derivatives. I think all of you studied this in your first year class. So I'll just try to remember the points. The basic name is haloalkane. Haloalkane. Halo may be what? Chloro, bromo, iodo, or fluoro. Alkane may be replaced by alkene or alkyne depending upon the type. See, CH3, CH2, CH2, Br. See, there is no double bond or triple bond, so this is an alkane. We have to apply our rules. What is the rule? If there is a functional group in a compound, we have to number the same so as to have the smallest number at the carbon containing the functional group. So this will be carbon number 1, this will be carbon number 2, this will be carbon number 3. We cannot number from this end. Okay? Why? Because we have to have a lower number, lowest possible number at the carbon containing functional group. So basically this is propane. At position 1 there is a bromine. So this is 1 bromo propane. Okay? What is this? This type of structure is called bond line representation. Bond line representation. Here you see, this is a methyl group, this is another methyl group. What is this? This is CH. So in this case, there is an iodine atom at position 2. This is carbon number 1, this is 2, this is what? 3. So its name should be 2-iodopropane. 2-iodopropane. So naming halogen derivative of alkene is not difficult. Let us have some names of haloalkene. These are haloalkanes. There may be haloalkenes. See. This is the parent chain. It has a double bond. So in this case, first let us number the chain. If we number from this end 1, 2, 3, bromine will come at 3. If we number it from this end 1, 2, 3, then also bromine will come at 3. So we can start number from this end or from this end, provided we consider only the position of bromine. But if such thing happens, we have to look at the position number of the double bond. See, if we number from this end 1, 2, 3, double bond comes at 3, bromine also comes at 3. But if we number from this end 1, 2, 3, then double bond comes at 2, bromine comes at 3. So we have to number from this end 1, 2, 3, 4, 5. We cannot number from this end. From left to right we cannot number. We have to number from right to left. So what is this? This is 3-bromo. Because bromine is at position 3. What is the parent hydrocarbon? Parent hydrocarbon contains 5 carbon. So 3-bromo pent. 3-bromo pent. What is the position of double bond? 2. So pent 2. Finally, in. What is in? In is the primary suffix for alkenes. An is the primary suffix for alkanes. So this is 3-bromo pent 2 in. Is that clear? Okay. In case of aromatic compounds, say we all know this is what? This is benzene. This is benzene. If there is a halogen atom, say chlorine here, what will be this? This is chlorobenzene. Okay. If there are 2 chlorines, this will be dichlorobenzene. But you have to mention the position of the 2 halogens, 2 bromines, 2 chlorines. This will be 1, 2 dichlorobenzene. Because this is carbon number 1 and this one is carbon number 2. See this one. Here, chlorine atom is at position 1, 2, 3, 4 and 4. So this will be 1,4 dichloro 1,4 dichlorobenzene. In case of aromatic compounds, when it is substituted by a single group, then different positions can be named as ortho, para and meta. You all know that. Look at this. Suppose this is an aromatic system, benzene. There is a group, suppose A here. So this is actually what? It is a substituted benzene. So with respect to the substitution A, this and these 2 positions are equivalent. This and these 2 positions are equivalent. And this position is unique. Is it not? It is unique. Now these 2 positions are called ortho. O for ortho. These 2 are called meta. M for meta. and this one position is called para. So in case of substituted benzene, we can have three types of positions: ortho position, meta position, and para position. So in that sense, these two positions are ortho. So this can be simply called ortho dichlorobenzene. Ortho dichlorobenzene. What is this? This is para dichlorobenzene. So these two names are also allowed. You see, para dichlorobenzene is a solid compound which is highly volatile. It is a compound with pleasant flavor, but it has a property called insect repelling property. Para-dichlorobenzene can repel the insects, different types of insects. So it is frequently used as insect repellent. Insect repellent. Now regarding naming of compounds, I will ask you one thing. You have to do, you have to practice a lot, because without practicing you cannot master this particular point. Okay, so I request all of you to practice more and more so that naming compounds becomes familiar. So now let us discuss methods of preparation of alkyl halides. So preparation of alkyl halides. See, already we have discussed what are alkyl halides, how are they classified, how are they named as per Iupac system. Okay, now we have to discuss the methods of preparation. We have to study the methods of preparation of alkyl halides. Say number 1. From hydrocarbons. Alkyl halides can be prepared from hydrocarbons. Number A, you see, from alkanes. See, an alkane is represented by, say, RH, when this is treated with chlorine, because all halogens do not react in this reaction. The alkane, when reacts with chlorine in presence of sunlight, diffuse sunlight, then that hydrogen is replaced by chlorine and HCl is produced. This is alkane, this is alkyl chloride. Now this reaction is called free radical halogenation. We have studied in class 11 that to methane, when reacts with chlorine in diffuse sunlight, we get chloromethane. So this is a general method of preparation of. So from hydrocarbons we can prepare alkyl halide. This is one method. Then come to number B, from alkenes. From alkenes. From alkenes also we can prepare alkyl halide. Look, RCH double bond CH2. This is a general alkene. When this is treated with hydrogen halide, say HBr, then This will give RCH CH3Br. This compound will be produced. This is called electrophilic addition. Electrophilic addition, and this reaction happens according to Markovnikov's rule. This reaction occurs according to the Markovnikov rule. What is that rule? According to Markovnikov's rule, when an unsymmetrical alkene is added with unsymmetrical reagent, then the positive part of the reagent adds to the carbon containing higher number of hydrogens. In this case, you see HBr is an unsymmetrical reagent. This alkene RCH11CH2, this is also unsymmetrical. So when we carry out the reaction, there will be Markovnikov's rule obeying. Now positive part of HBr is H. So according to Markovnikov's rule, H will add with this carbon. Because this carbon has one hydrogen, it has two hydrogens. So according to Markovnikov's rule, positive part of reagent adds to that carbon which has higher number of hydrogens. Okay. So hydrogen acts with this carbon, bromine acts with this carbon. As a result, we have this product. Consider this example. Say CH3CH double bond CH2. What is this? This is propene. Add HBr. On adding, you will have CH3CH3Br. This is 2-bromopropane. 2-bromopropane. So, regarding Markovnikov's rule of electrophilic substitution, you have studied in your class 11. If you have any doubt, then please go through that part of your class 11 book. Okay, Markovnikov rule. In this case, there is another type of reaction. It is anti-Markovnikov rule. This is also called Peroxide Effect or Kharas Effect. Peroxide Effect or Kharas Effect. This happens only when there is some peroxide in the reaction mixture, because we all know that addition of HBr to propene or any other alkene is electrophilic addition. But whenever we put some peroxide in the reaction, the mechanism of the reaction shifts. The mechanism of the reaction changes. The mechanism changes from electrophilic to what? To free radical. Okay, so we'll discuss that part. Say, consider this reaction, propene plus HBr in presence of say peroxide. In this case, we will get anti-Markovnikov product. We will get anti-Markovnikov product, that is 1-bromopropane. Okay, 1-bromopropane. See, we can have alkene halides from hydrocarbons. We have two types from alkanes. There is only one reaction. That reaction is free radical substitution reaction. From alkenes, we may have haloalkanes. Simply by electrophilic addition of hydrogen halide to alkene or addition of hydrogen halide to alkene in presence of peroxide. But there is one important point. That point is that you are to observe anti-Markovnikov's rule only when there is HBr as a hydrogen halide. This rule is not obeyed by hydrogen iodide or chloride. Okay, HCr, HI, in this case, peroxide effect will not be applicable. We may have dihaloalkanes from alkenes. See, CH211CH2. This is what ethene. Okay, when you add bromine, then you will get CH2CH2. A bromine will be entered here. The other bromine will be here. What is this? This is 1,2-dibromo ethane. Okay, 1,2-dibromo ethane. So using this reaction, we can produce monohaloalkane as well as dihaloalkane. See, hydrocarbons may be alkene. We may have some aromatic hydrocarbons also. Okay, so there is another reaction here. We can prepare alkene halide from aromatic hydrocarbons also. From aromatic hydrocarbons. We all know that what is the simplest aromatic hydrocarbon? This is benzene. Now, if benzene is treated with chlorine in presence of FeCl3, ferric chloride catalyst, then we get chlorobenzene. We get chlorobenzene. This reaction is an example of electrophilic substitution. Electrophilic substitution. Here chlorine Cl2 reacts with FeCl3 to produce a electrophile. That electrophile then attacks the benzene nucleus and thereby you get chlorobenzene as a product. In this way, starting from alkane, we can produce alkyl halide by means of free radical halogenation. Starting from alkene, we may get alkyl halide by means of electrophilic addition, and if you use peroxide, by means of free radical addition. From aromatic hydrocarbons also, we can prepare haloarenes. This is actually halobenzene, chlorobenzene. This is haloarene. So aromatic hydrocarbons produce haloarenes, and this reaction is electrophilic substitution. So in this case, if we study this particular point, method of preparation of alkyl halide from hydrocarbons, we have got three types of reactions. We have got three types of reactions. Type 1. What is this? Free radical substitution. Okay, free radical substitution. Type 2. This is electrophilic addition. Electrophilic addition. Type 3. Electrophilic substitution. Not 3 actually, we have 4 types of reactions. Another type we have got, it is free radical addition. This is electrophilic addition. This is seen in case of reactions obeying Markovnikov's rule, and this type of reaction, free radical addition, this is seen in case of anti-Markovnikov's addition or peroxide effect. Peroxide effect. In this way, From this particular point, we have got 4 different types of reactions. Now we have to discuss, we have to study the mechanisms of all those reactions. First, let us discuss the mechanism of free radical substitution. Mechanism of free radical substitution. For this purpose, we will consider chlorination of methane. Chlorination of methane in diffuse sunlight. Chlorination of methane in diffuse sunlight. The reaction is this: CH4 plus Cl2 in diffuse sunlight. It yields CH3Cl plus HCl. What is the mechanism? The mechanism of the reaction is like this. See, initially due to the absorption of photon, chlorine molecule will undergo homolytic cleavage, and thereby 2 chlorine free radicals are produced. What are these 2? Chlorine free radicals. Okay. So this is the initial step of the reaction. Chlorine molecule absorbs sunlight, and by absorbing sunlight it gets homolytically cleaved. As a result, 2 chlorine free radicals are produced. Then that chlorine free radical, we all know that free radicals are highly reactive species. Being highly reactive, it will instantly react the alkene, react with the alkene. The alkene is methane. Let us write methane like this: CH3 single bond H. The chlorine free radical attacks the methane molecule. What happens? See, this electron is used for the attack by chlorine. This is a sigma bond. There are 2 electrons. One electron will be going with this electron from chlorine. The other electron will go to carbon. Since this process is homolytic cleavage, this is also a homolytic cleavage. As a result, we will get what? CH3 dot plus HCl. What is this CH3 dot? This is methyl free radical. Methyl free radical. In the next step, that methyl free radical will attack another molecule of chlorine. Look what happens. This electron will be used by methyl group for the attack. This bond will undertake homolytic cleavage. As a result, we get CH3Cl plus Cl dot. Now these 2 steps, they are called propagation. This step was initiation. This one is initiation. So in propagation, what happens? One chlorine free radical will attack a methane molecule, thereby producing a methyl free radical. That methyl free radical then attacks another chlorine molecule, producing methyl chloride and another chlorine free radical. Now this chlorine free radical will attack another methane molecule which is in the system. As a result, these 2 reactions, they will proceed like a chain reaction. You see, one radical consumed generates another radical. Chlorine free radical is consumed, methyl free radical is produced. Here methyl free radical is consumed, again chlorine free radical is produced. That chlorine free radical will then attack another methane molecule. So these 2 steps will continue until all the methane and chlorine gets finished. Then in this type of reaction, there is another step called termination. What is termination? In termination step, the reactive free radicals will dimerize, and thereby they become inert. In termination, what may happen? Any two reactive radical may dimerize. Say, methyl radical combines with another methyl radical, will get what? Ethane. Methyl radical may combine with chlorine radical, will get what? CH3Cl. So such steps, they are called termination. Such steps are called termination. See, this is a chain reaction actually. Free radical substitution. This reaction is a chain reaction. Chain reaction. And for chain reactions, there are three steps. Always there are three steps: initiation, propagation, termination. In initiation, the chain will be initiated, started. In propagation, the chain will be elongated. It will be continued. In termination, the chain will be closed, ended. Now, initiation may occur by means of application of light energy or heat energy. In this case, because light energy or heat energy can favor homolysis of chlorine-chlorine bond. Light energy is better. Light energy is better because to carry out homolysis of chlorine molecule, that molecule is to be heated to a very high temperature. It will be a costly process. So this is not costly at all. Simply you have to take some chlorine, mixture of chlorine and methane, and you have to irradiate it. Direct sunlight is not necessary. Simply diffuse sunlight is enough. That initiation results in formation of chlorine free radicals. Then chlorine free radical will enter into the propagation step. So what is seen here? Only one free radical produced in the step 1, initiation, may result in producing a huge amount of product, because initially you have to irradiate that reaction mixture, but after irradiation, as soon as some free radicals are produced, then no further irradiation is required. You may keep it in dark. In dark also the chain reaction will proceed. So in this way we can explain the mechanism of free radical chlorination of methane. It is a chain reaction, but there are some disadvantages also. Advantages are there because no say further heating or such type of say increasing temperature, pressure, etc. these are not required. Simply you have to irradiate. But there are some disadvantages also. What are the disadvantages? The most prominent disadvantage of free radical chain reaction is that in this particular type of reaction, always we have mixtures of product. You see how mixtures are produced. Say there is a chlorine free radical. It may attack methane. That chlorine free radical, methane, what will happen? CH3 dot plus HCl. That CH3 dot will attack another molecule of chlorine, will get CH3Cl plus Cl dot. These two steps are already discussed. Now that chlorine free radical which is generated may attack methane as well as this CH2ClH. This is chloromethane, methyl chloride. In methyl chloride there are 3 hydrogens. So that hydrogen may be abstracted by chlorine free radical. In that case what we have? We have CH2Cl dot plus HCl. Then CH2Cl dot. This will react with chlorine. In this case, we will get CH2Cl2 plus Cl dot. So in these two steps, first two, we get chloromethane, but here we get dichloromethane. Similarly, chlorine free radical may may affect dichloromethane also. Then this will lead to formation of chloroform, trichloromethane. Again, if chlorine free radical attacks trichloromethane, it will lead to formation of carbon tetrachloride. So all these different types of halogen derivatives will be produced here. We cannot limit the reaction in getting only one type of product. We can produce the reaction will yield different types of chlorine derivatives. Methyl chloride, methyl chloride means chloromethane, dichloromethane, trichloromethane, tetrachloromethane, etc. Again, you see in termination step, suppose this radical dimerizes with this radical, methyl dimerizes with, combines with this, then what? We will get one chloroethane. If two such radicals dimerize, we will get 1,2-dichloroethane. So there is numerous possibility of products. So this is the disadvantage associated with such reactions. Such reactions are easy to be performed, but disadvantage is that it usually leads to what? A huge number of products. Let us now discuss the type 2. Type 2 reaction, mechanism of the type 2 reaction. What is that type? Mechanism of electrophilic addition. For this purpose, we will consider this reaction CH3CH double bond CH2. This is propene plus HBr. This will give you CH3CH3Br. This is 2-bromo-propane. This is major product. Another product is possible. That product is the anti-Markovnikov product. This is Markovnikov product. The anti-Markovnikov product will be 1-bromo-propane. That product will also form to some extent. See what will happen here. This is the olefinic double bond, so C double bond C. Okay. What is this double bond? This is actually what? There is a sigma skeleton. It is planar. Okay. Now above and below the plane, there is a pi bond. So this is actually this. Again, what is this? If this is a planar arrangement, there will be a lobe here and another lobe here. So you remember this point. In alkenes, there is a carbon-carbon double bond. A carbon-carbon double bond means above and below a sigma skeleton. This is the sigma skeleton, a planar arrangement. Above and below that arrangement, we have loosely held pi electrons. Loosely held pi electrons. These are called pi electron clouds. Loosely held, because a pi bond is weaker bond compared to sigma bond. Now see, by virtue of the loosely held pi electrons, what can an alkene do? It can attack electrophile. How is it possible? Let us see. This is an alkene. Suppose there is HBr. It is a covalent molecule, but electronegativity difference between hydrogen and bromine leads to a polar covalent bond. So that bromine is what? Delta minus, hydrogen is delta plus. Now, by virtue of the loosely held pi electrons, the alkene will attract the hydrogen end of this dipole. It is a dipole, positive, negative. As a result, what will happen? This hydrogen could make a bond with either this carbon or with this carbon. If hydrogen forms a bond with this carbon will be positive. Otherwise, if hydrogen forms a bond with this carbon, then this carbon will be positive. So such an arrangement will be obtained. Plus what? Plus Br minus. See, as soon as the pi electrons attack the hydrogen end, this bond will break. Bromine becomes negative. This hydrogen is positive. That positive hydrogen will attach with this carbon, leading to positive charge at this carbon, or this hydrogen attached with this carbon, leading to positive charge at this carbon. Okay. So this is the step 1. In step 1, what is formed? A carbocation is formed. Carbocation is formed. In the next step, what will happen? That carbocation, we consider this one. Say this is the carbocation. This carbocation will be attacked by bromide. Bromide will definitely attack at the positive end. Okay, and this will give you this. In this connection, you remember one thing. Actually, this arrow should not be placed like this. Okay, because you see, this hydrogen is delocalized over one face of the alkene. Okay, if this is the alkene, the carbon skeleton lies suppose along this plane, then there will be hydrogen above this plane. The hydrogen may bond simultaneously to this carbon and also to this carbon. In that case, bromide ion cannot attack from the upper face. Is it clear? So what bromide ion will do? It will attack from the opposite face. Bromide ion will attack from the opposite face. So the arrow should be placed like this. This type of addition is called what? Remember, trans addition. Trans addition. Now we will verify the applicability of Markovnikov's rule. Okay. So this was our reaction, addition of propene with HBr to produce 2-bromopropane as the major product. We will verify the validity of Markovnikov's rule. See, CH3CH double bond CH2 plus HBr. This is step 1. H is delta plus, Br is delta minus. Now alkene, the double bond, pi bond will attack the hydrogen end. So bromine will leave as Br minus. Now what can happen? This hydrogen may bond to this carbon. In that case, this carbon will be positive. So CH3, CH, CH2, this carbon is positive. Or if hydrogen forms a bond with this carbon, then CH3CH CH2H. In this case, this carbon will be positive. Is that clear? Hydrogen may form a bond with this carbon. In that case, this carbon will be positive. But if hydrogen forms a bond here with this carbon will be positive. So this is suppose 1 and this is 2. Both are carbocations. Is it not? It is carbocation, this is also a carbocation. Now between these two carbocations, tell me which one is more stable? Between these two, which one is more stable? We know that this is a primary carbocation. The cationic carbon is primary because it is CH2. But this one is secondary, it is CH. Okay? So 2 is more stable. Carbocation 2 is more stable than 1. Why? Because it is a secondary carbocation. It is a secondary carbocation, while 1 is primary. So compared to primary, secondary carbocation is more stable, and compared to secondary, tertiary carbocation is more stable. So carbocation 2 is more stable. So if in a reaction there is possibility of getting more than one product, and among those different products, if one product is more stable, then that product will be formed in greater amount. Between 1 and 2, 2 is more stable, so it will be formed predominantly. Hence, 2 is formed predominantly. Okay, 2 is formed predominantly. So between 1 and 2, amount of 2 will be higher in the mixture. So what is this? This is step 1. In step 2, what will happen? Both of these two will be attacked by the nucleophile. The nucleophile is what? Nucleophile is Br minus. This to be written here. So in the step 2, both 1 and 2 will be attacked by bromide. But since there is greater amount of 2, it will be attacked to greater extent. CH3, CH, CH3 plus. This is carbocation 2. This will be attacked by bromide. This will give you CH3, CH, CH3, Br. So this is major product. Minor product will be given by 1 because there is little amount of 1 also in the mixture. So little amount of 1 will give you the minor product. So in this way, we can verify the validity of Markovnikov's rule. Now let us pass on to type 4. It is free radical addition. Free radical addition. See, this is the case when we use peroxide. So let us say peroxide effect. The same reaction, say propene plus HBr in presence of peroxide gives 2CH2Br, 1 bromopropane as the major product. Okay. Now we are going to discuss the mechanism of this reaction. See, in peroxide there must be a linkage of this type. O bond, single bond, O. Consider hydrogen peroxide. Hydrogen peroxide is what? H2O2, HOOH. If you replace these hydrogens by some alkene groups, then this is an organic peroxide. So there may be some alkene groups. Say R dash. This is organic peroxide. Peroxide linkages are very weak bonds. Therefore, they are prone to homolytic cleavage. homolytic cleavage of this will result in what? RO dot plus OR dash. This type of free radicals containing oxygen. Now you see oxygen, we know oxygen has a very strong desire for hydrogen. So whenever there is a radical at oxygen, that radical oxygen will be highly capable to abstract hydrogen from anywhere else. Now here you see in HBr, here is hydrogen, is it not? Now oxygen radical has the capacity to abstract hydrogen, so it will abstract hydrogen from HBr. As a result, what will happen? That hydrogen comes to oxygen plus what? Br dot. This time bromine free radicals are produced. Bromine free radicals are produced. So in the earlier case, in case when we do not add peroxide, the attacking agent was H plus. So that reaction was electrophilic addition. But here the attacking reagent is same. It is Br dot. It is a free radical. So look, what will happen now? Now Br dot will attack the alkene. CH3 CH double bond CH2 plus Br dot. What will happen? See, in this case also the pi electrons will be used. There are 2 pi electrons, one of the 2 pi electrons will be used, the other will be remain. You see, one of the 2 pi electron is used to form a bond with bromine. So bromine in this case also CH3 CH2. Suppose bromine, look. Suppose bromine adds with this carbon. In that case, this will be free radical. This will have odd electron. This is say 1. There is another possibility. What is that? CH3 CH2Br. Now bromine adds with this carbon. Then radical will be here. So in this case also there are 2 possibilities. This is one possibility, we get radical 1. This is another possibility, we get radical 2. Now between these two, which one is more stable? This is a primary free radical CH2 dot. This is a secondary free radical CH dot. Okay. So free radical 2 is more stable, okay, compared to 1. Free radical 2 is more stable. Being more stable, hence 2 will be formed in higher amount. 2 will be formed in higher amount, okay. In the subsequent step, what will happen? CH3 CH dot CH2Br. This will attack another HBr molecule to get what? To give what? CH3 CH CH2Br plus Br dot. See, this radical carbon abstracts hydrogen from HBr. This hydrogen goes to this carbon, carbon number 2. Bromine, because bromine is already at carbon number 1. This gives you 1 bromopropane. This is the major product. So the nature of major product is controlled by the type of mechanism. In case of Markovnikov's addition, the mechanism is electrophilic addition. But in case of peroxide effect or Kharas effect, that is in case of anti-Markovnikov's rule, the mechanism of the reaction is free radical addition. Remember these 2 points. So we have discussed 3 types of mechanisms, mechanisms of 3 types of reactions. Now we will discuss type 3 electrophilic substitution. Mechanism of electrophilic substitution. Mechanism of electrophilic substitution. Okay. For this purpose, we will consider this reaction. Say benzene plus chlorine in presence of ferric chloride catalyst to produce chlorobenzene plus HCl. Here, efficiently ferric chloride is a Lewis acid. It acts as a catalyst. You see, ferric chloride helps in generating the electrophile. Being Lewis acid, it can accept an extra pair of electron. As a result, what will happen? You will have Cl plus FeCl4 minus. This is chloronium ion. This is the actual attacking agent. Now that chloronium ion, the attacking electrophile, will attack the benzene ring. What will happen? See, the pi bond of benzene will attack the chloronium ion, thereby producing this. Now there is possibility of resonance. This bond say moves over here. In that case, positive charge will move to this position. Another resonance possibility. Okay. So this pi electron from benzene attacks the electrophile, thereby producing this type of a species. That species is a hybrid of all those possible structures. What is this? This is actually a hybrid of these 3 possibilities. We can denote the hybrid as this. You look one thing, the positive charge is all over the species except at this carbon. At this carbon there cannot be a positive charge because it is a tetravalent carbon. 1, 2, 3, 4. So except this carbon, the positive charge is distributed all over the molecule. So we will put a positive sign here, and the delocalization of the positive charge will be denoted like this. Okay, this is called a sigma complex. Except this carbon, the other part positive. This is called a sigma complex. So what happens here? Initially there is generation of chloronium ion. This is the attacking electrophile. Then in the next step, chloronium ion attacks benzene, thereby producing a sigma complex. In the final step, what will happen? There will be loss of proton by the sigma complex. We may consider any one of these 3 structures. So let us consider the first structure. What will happen now? This bond between carbon and hydrogen, this is a sigma bond, it will be converted to a pi bond between carbon and carbon. Proton H plus will be lost. H plus will be lost. So this is step 1 and this one is step 2. This step 1 is slow while this one is fast. Second step is fast. Finally, the ferric chloride catalyst will be regenerated by reacting with H plus. H plus will react with FeCl4 minus to produce HCl plus FeCl3. H plus FeCl4 minus, this will give you H plus FeCl4 minus, this will give you HCl plus FeCl3. The catalyst is regenerated. That catalyst can be used up again for the reaction.